Okay, so ultimately the EMF is negative the change in magnetic flux, right, over time, right? A magnetic flux is number of windings times B times A times the cosine of the angle. Okay, and let's assume that that it's into the page, out of the page, that this angle is actually 0 degrees, right? It's all of the flux lines are going through that loop, right? Okay, and so this guy is going to go away. This guy doesn't change, and so it's NBA over whatever the time is, right? And there is only one winding here. Now, if there was many, many windings, we'd get this much EMF from every single winding, and that's why there's an N there, right? But in this problem, it's just it looks like it's just BA, right, over T. So to get the and it's the, in this case it's the change in magnetic field, right? So to get this answer here, I'm going to go the change in magnetic field, right, which is 0.249 minus 0.142. And I'm just doing this to get a positive number. Okay, and then my area is pi times 2.5 squared. And then the time is 0.621. Okay, and these are Teslas, and that's meters, right? Okay, so if I put that in my calculator, I get, yes, it says my batteries are low. 0.249 minus 0.142 times pi times 2.5 squared divided by 0.621. And I get 3.3831, or 3832, I guess. Okay. And that is volts, right? The EMF is in volts. And as far as I can tell, EMF is, you can divide by resistance and get current. So it's just like voltage. Okay, so what does EMF induce? Which way does the current flow? Well, let's see. It is the magnetic field. It's into the page, and it's decreasing, right? So it's one of these things, right, where we've got magnetic field decreases, B decreases. Oh, no. B increases. Sorry. It goes from this to this, right? Okay. So B is increasing, and so the let's see, if we gain into the page, we oppose that by making out, right? And the way to make flux out of the page is to go clockwise, anti-clockwise, sorry. Okay, so I'm wrapping my fingers anti-clockwise, my thumb is out of the page, right? So it's going to be an anti-clockwise, right? Or another way to do it, right, is if you imagine that north pole of the magnet coming down toward the page, you don't want it to approach, so you create a north pole magnet facing out of the page with this, and that opposes the motion of the magnet, okay? Then it says, what's the current that flows, okay? Well, okay, to get the current that flows, I'm just going to use Ohm's law, right, which is current is V over R, or something like that, right? Okay, so 3.3832 divided by 2.3 ohms, right? That's volts over ohms. So I just divide that guy. Wait, let's go. Okay, and then I'm going to divide by 2.3. I'm going to store that guy too, and I get 1.4709 amps, and that's my current that's flowing, right? And then there's all these other questions, and these other ones up here on the test. So let's go on and do those guys. Okay, what is the power dissipated? And here are our answers right there from before, right? The power I'm going to use for power, I think I'm going to use V squared over R. I could use I squared R, I could use I times V, but multiply these guys, but I'm going to just choose this guy here, right? So that's going to be 3.3832 squared divided by 2.3, okay? Now if you get a slightly different answer from me, that's because I'm using like unrounded things in my calculator. Okay, I'm going to store that guy and see. So if I do that, I get 4.9764 watts, right? Okay, that's my power, right? Then it says, what is the total electrical energy generated? Well, power is work divided by time, so work is power times time, and that's 4.9764 96 or 9764. That's joules per second, and then this whole thing, if you recall, took 0.621 seconds. That's from the previous thing, right? Okay, so I'm going to go times 0.621, and I get that the work, or the energy evolved, is 3.0904 joules, right? So I get that, right? And then it says it moved 3.75 centimeters to affect or cause this change, right? What is the average force? Well, to get force, I'm going to say work is force times distance, right? Okay, so force is work divided by distance. So here's our work, 3.0904 Newton meters divided by, and then we got to turn that into meters, 0.0375 meters. So divided by 0.0375, it's 82.409 newtons of force, right? So the concept here is that this energy came from the fact that we had to exert a force times a distance on this object to make it move, right? Okay, so that's the idea. That's the concept here, okay? Is that it's conservation of energy. This electrical energy doesn't come from nowhere, okay? It comes from the work that we did. The fact that it has to oppose the motion, this is Lenz's law, okay? The fact that it has to oppose that motion is conservation of energy. Electrical energy doesn't come from nowhere. It comes from the work you do to change the flux. I have to go sing for Duggan's class.